So it's another collection of functions where we can talk about the function and its derivative, and we are skipping that section. Okay, so 3.7, the topic is L'Hopital's rule. And what you might notice is that what I have written up here on the board, H-O-P-I-T-A-L, L'Hopital, okay, is not the way it's written in the book. And the way it's written in the book, we have L, and then it's actually L hospitals rule. And it turns out that depending on what textbook you look in, you may or may not see the S, and so I happen to have learned it without the S, so I always call it L'Hopital's rule. Our book uses the S. Either way, it's pronounced L'Hopital's, it is not L Hospital's rule, so it sounds foolish if you're walking around and saying, today in class we learned about L Hospital's rule. Okay, so party foul, seriously. So be careful about that. So this is called L'Hopital's rule. Now, what's happening here is we're actually coming full circle from the beginning of the class. At the beginning of the class, we studied this idea of limits in order to be able to come up with the limit definition of a derivative, and that allowed us to come up with formulas to calculate derivatives. It turns out, once we understand derivatives, that we can actually use derivatives to go back and help us understand limits better. Okay, so we're kind of going in a circle. So section 3.7 is using derivatives to help calculate limits. All right, now early on in the semester when we first began talking about limits, you may have seen a problem similar to this, calculating the limit as x approaches 2 of x squared plus x minus 6 divided by x minus 2. And so the idea was if we wanted to calculate this limit algebraically, the very first thing we might do is check to see what happens if we plug 2 into our expression. And so I might have a thought bubble over here. In the numerator, I've got 4 plus 2 minus 6, and in the denominator, I end up with 2 minus 2. So in the end, if I plug in my limiting x value right away, I get 0 over 0. And what that tells me is that I should keep working with this until I can factor out an x minus 2 on the top and cancel it with my x minus 2 in the bottom. So 0 over 0 told me keep doing some algebra and see if we can do any sort of factoring. So on the top, well, then we do factor, and so we get x minus 2 times x plus 3, and then we have x minus 2 in the denominator. The x minus 2's cancel. We're left with the limit as x approaches 2 of x plus 3, and since we no longer have a denominator to worry about, we can go ahead and take this all the way to the limit, allow x to be equal to 2, and we end up with 2 plus 3, which gives us 5. So the meaning of this limit was as x gets close to 2, the y value of this function is approaching 5. All right, so that was one of our limits. Are there any questions about that? All right, so another one that we looked at, and we used a table of values to come up with our answer, was the limit as x approaches 0 of sine x over x. And we looked at a graph of this function, and we said as x gets really close to 0, the y value of sine x over x approaches 1, and so our limit is equal to 1. And we used this limit strictly based on our graph and our table of value version. But if I go back to this sine of x over x before we know that this limit's equal to 1, then I have sine of 0 over 0 if I plug in my limiting value, and we get 0 over 0, but I can't really do any algebra to fix that, so we went to our table of values. All right, so algebraically, when we had 0 over 0, we could factor and eventually get a final answer, and that was nice. When we got 0 over 0, in the case with the sine x, we had to default to the graphical method of coming up with the limit was equal to 1. It turns out that this mathematician named L'Hopital, he came up with an idea that allows us to calculate this limit in a way better way. So in order to do that, we need to talk about a few definitions. If I have a limit as x approaches a of f of x over g of x, and if the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0, then we say that the limit is an indeterminate form. And in particular, if when we plug in the a into the top and into the bottom we get 0 over 0, we say that the limit is an indeterminate form of type 0 over 0. So both of these limits over here, the limit as x approaches 2 of x squared plus x minus 6 over x minus 2, this limit, as well as limit as x approaches 0 of sine x over x, these are both indeterminate forms because when we allow x to go all the way to 0, we get a 0 in the numerator and the denominator. So we get 0 over 0 in both of these cases. We can also have indeterminate forms that are of other types. So, other types of indeterminate forms. We can have, as an example, the limit as x approaches infinity of natural log of x over x. When I think about these two functions, natural log of x over x, as x gets really big, natural log of x, well, that graph is going uphill. And so as x gets really big, natural log of x also gets really big. And as x gets really big in the denominator, well, the denominator, which happens to be equal to x, also goes to infinity. And so if I have a limit where I have a fraction, and the top of my fraction goes off to infinity, the bottom of my fraction goes off to infinity, we say that this limit is an indeterminate form, and it's an indeterminate form of type infinity over infinity. So that's a good question. Is infinity over infinity equal to 1? And the answer is sometimes, but not always. So every once in a while, infinity over infinity is equal to 1. In this particular case, infinity over infinity happens to be equal to 0. So infinity over infinity, because it's unclear what that means, that's why it's indeterminate. We don't really know what infinity over infinity means. Okay, so there's that example, and one final example. The limit as x approaches infinity of 1 minus e to the x over x to the third. In our denominator, as x goes to infinity, as x gets really big, certainly x to the third is going to get really big as well. And in the numerator, as x gets really big, the only thing that's changing in my numerator as x gets big is this e to the x. And so as x gets really big, e to the x is getting really big also. But we have 1 minus something really large, which means that as x goes to infinity, our numerator 1 minus e to the x is going off to negative infinity. So thinking about this one up here, we have 1 minus a really big number. Well, that 1 is pretty much insignificant, and I pretty much have a negative really big number. Okay, so this particular limit is of the form negative infinity over infinity. Okay, are there any questions about the definition of indeterminate form? An indeterminate form is a limit that if we analyze what happens as x approaches the limiting x value, we either get 0 over 0 or infinity over infinity, or plus or minus infinity over infinity.
So it can be any combination of that.
Right, any combination of plus minus. What we cannot have a combination of is 0 and infinity. Okay, so now that we have that definition, then we can write down L'Hopital's rule. So here is what the mathematician says. So L'Hopital's rule says that we're going to consider the limit as x approaches a of f of x over g of x. So this is what we're looking at calculating. A limit as x approaches some number, and we're looking at a fraction, a function divided by a function. Now suppose, number one, that our functions f and g, the numerator and the denominator, are differentiable. We are also going to suppose that the limit as x approaches a of g prime of x is not equal to 0. It's not clear why that's useful, but we're going to throw that in there. And we are going to suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0. Or the limit as x approaches a of f of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is equal to plus or minus infinity. Okay, so we haven't quite written down L'Hopital's rule. These are our hypotheses. So the first hypothesis is that our numerator and denominator must both be differentiable, meaning that we can find derivatives of the numerator and the denominator. This other rule over here, well, this says that either we have an indeterminate form of 0 over 0, or we have an indeterminate form of infinity over infinity, possibly with a plus or minus in front. All right, so L'Hopital's rule applies when we have differentiable functions, and when we plug in the limiting x value, we end up with either 0 over 0 or infinity over infinity. Now this rule is going to, we'll see why that's here in a minute. Okay, so those are our hypotheses. If we don't satisfy these hypotheses, we cannot use L'Hopital's rule. But here's what L'Hopital says. So if all of those things happen, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime provided this limit exists. Or is plus or minus infinity. All right, so L'Hopital's rule says that if you have some limit you're trying to calculate that's two functions divided by each other, and when you plug in this x value that we're allowing x to approach, so we plug that into the function on the top and the bottom, and we get either 0 over 0 or infinity over infinity, then one way to calculate that limit is to take the derivative of the top and the derivative of the bottom, and our limit will be exactly the same. So the limit of the ratio of our functions is the same as the limit of the ratios of their slopes. That's what L'Hopital says.
Do you have to do the quotient rule, or you just boom top, boom bottom?
Yeah, so this is not the quotient rule. So we're not saying that the derivative of f over g is f prime over g prime. We're saying that the limit of their quotient is the same whether you have the original function or the derivatives. Okay. So yeah, so be careful not to mix this up with the quotient rule.
Okay.
Now this is why this extra piece is in here, because our new value here is going to be, we need to make sure that we don't end up with a 0 in the denominator. Okay, so that's what this extra suppose here in the front is for. Okay, so let's take a look at some of these examples. So the very first example that I put up on the board was the example of the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. And when we plugged in x equal to 2, in the numerator we got a 0, and in the denominator we got a 0. And so this limit is an indeterminate form. It's of type 0 over 0, which means that we are allowed to use L'Hopital's rule. All right, now L'Hopital says that the limit of my original function up here is exactly the same as if I take the derivative on the top, 2x plus 1, and the derivative on the bottom, which is 1. And now if I simplify this limit, I've got the limit as x approaches 2 of 2x plus 1. And this is sweet because now I don't have any denominator, and I can go right ahead and allow x to go all the way to 2. And so I've got 2 times x, which is 2 plus 1, which gives us 5. So we came up with the same limit value as we did when we factored and canceled. This was our step right here where we used L'Hopital. All right, the second example that I wrote up on the board was looking at the limit as x approaches 0 of sine x over x. And in terms of calculating this limit, if I allow x to go all the way to 0, then I end up with 0 over 0. And so we have an indeterminate form, and I may use L'Hopital. And so when I use L'Hopital's rule, I've got the limit as x approaches 0. We're going to take the derivative in the numerator. So derivative of sine x is cosine x. And my derivative in the denominator is 1. So this is great because now my denominator is pretty much irrelevant. And we have the limit as x goes to 0 of cosine x. Now we can take this all the way to the limit. As x goes to 0, we end up with cosine of 0, which is 1. And so using L'Hopital gives us a legitimate way to show that the limit as x approaches 0 of sine x over x is equal to 1. All right, are there any questions about either of those two examples?
Look at third.
The third one, this one, or that was the fourth one?
Well, yeah, that one.
Okay, I'm gonna hold off on that one. Let's look at the third one first and the fourth one.
Okay.
See what happens. All right. The next one that I had you look at was the limit as x approaches infinity of natural log of x over x. And when we looked at this one, we decided that this limit was an indeterminate form of type infinity over infinity. And the reason that we know this is because as x gets really big, our denominator is getting big. And as x gets really large, natural log of large numbers are also large. Okay, so as x gets big, natural log of x also gets big. So we have type infinity over infinity. We have an indeterminate form. And so we can use L'Hopital. All right, so L'Hopital says our original ratio, the limit as x goes to infinity, the original ratio is the same as the limit of the derivatives. So derivative of natural log of x is 1 over x. Derivative of x is 1. And so we've got the limit as x goes to infinity of 1 over x. So what happens to 1 over x as x gets really big?
It's really small.
Yeah, this gets really tiny. And so 1 over x goes to 0 as x goes to infinity. So our limit is equal to 0. Now, this is interesting because here, this idea of infinity over infinity, I mean, if we want to talk about that as a number, here infinity over infinity is equal to 0. Whereas in some other examples that we're going to see, we may not get 0 as an answer. Infinity over infinity in this case is 0. Now, what does this 0 tell us? What it tells us is that as x gets really big, the numerator is trumping, I'm sorry, I'm pointing at the denominator. The denominator is trumping our numerator. So our denominator is getting large much faster than our numerator. So the numerator is small in comparison to the denominator. And so our final limit is 0. All right, so the example that you wanted to see. We've got the limit as x approaches infinity of 1 minus e to the x over x to the third. And so our denominator, it turns out, is, as x gets really big, our denominator is getting big. So x to the third goes to infinity. And in the numerator, we have 1 minus a very large number, so 1 minus e to the x goes to negative infinity. So our form is negative infinity over infinity. That is one of our indeterminate forms. Which means that we can use L'Hopital. All right, so L'Hopital says we're going to take the limit as x goes to infinity. In our numerator, derivative of 1 is 0. Minus the derivative of e to the x, which is e to the x. Denominator, derivative is 3x squared. All right, any questions about that step right there? We just applied L'Hopital. All right, so I look at this now and I say, okay, what am I going to do with this? I don't know. So I look at it again and and I say, well, what kind of a fraction do we have here? And if I analyze this whole limit, as x gets really big, my numerator is getting really big in the negative direction. So our numerator is going off to negative infinity. What about our denominator? Yeah, this is getting really big in the positive direction. So our ratio here, our limit, our overall limit, is still an indeterminate form, which means that we get to go on a second date with L'Hopital, and we can use L'Hopital again. All right, so here we go. We're going to hit this function with L'Hopital again. We've got the limit as x approaches infinity. In the numerator, we still have negative e to the x. And in the denominator, we have 6x. Okay? So I look at this limit and I say, what am I going to do with this? Yeah, still not really sure what to do with this. So if I allow x to get really big, our numerator is still going off to negative infinity, and our denominator is still getting really big in the positive direction. So I get to use L'Hopital again. After using L'Hopital a few times, you start to fall in love with L'Hopital. So here we go. We get to use L'Hopital again. And we've got the limit as x approaches infinity. Derivative of our numerator is still negative e to the x. Derivative in the denominator is 6. Now we're very happy. So we cheer because we no longer have anything changing in the denominator. In fact, if you really, really, really wanted to use L'Hopital again, you really, really, really should not. Because as x gets really big, the numerator goes to negative infinity, but the denominator stays at 6. And so this is not a place to use L'Hopital. Nor would we want to, because at this point, in our denominator is just plain old everyday 6, and our numerator is going to get very, very large in the negative direction. And so very large negative number divided by 6 is still a really large negative number. So our final limit is negative infinity. So we've now used L'Hopital's rule in 4 different examples on the board. One of the examples, we ended up using L'Hopital repeatedly. Each time it got rid of one of our x's in the denominator until we were left with just a plain number, and then we can analyze our L'Hopital. Not our L'Hopital, our limit.
So before we said that taking the first, second, and third derivative was changing, our tangent line going from points to velocity to acceleration. Are we doing anything similar to this, or are we just simplifying?
So here, what's happening is in the first ratio, we're comparing y values of the top function versus the bottom function. In the second one, after we've taken the derivatives, then our limit is comparing the slopes of those functions.
Mm-hmm.
And then the next one, we're considering the slope of the slope and comparing how those two values change as x gets really big. And then if we do the derivative again, we're looking at the slope of the slope of the slope.
So the slope of the slope of the slope is really just the slope?
The slope of the previous expression.
Which is the slope of the previous?
Yes. Yes.
I have a question. So what would you do if you had something that really you kind of simplify like that? Let's say if you had like sine x minus x to the, or e to the x over cosine plus e to the x.
So sine of x minus e to the x over
Cosine
of x.
plus e to the x?
And is it the limit? Okay, so we're taking a limit then as x approaches infinity?
Sure.
Okay. So, let's see here. So the first thing is, this is going to be a little bit of a funny one, right? I mean,
Would you have something like this?
well, let's see what's going to happen here. So if I did this, as x goes to infinity, on the top, we've got, and this would be a little bit tricky because I've got some number between -1 and 1 minus some really huge number. So I could maybe argue that I've got a negative infinity on the top and a positive infinity on the bottom. So if I tried to use L'Hopital's rule, take the limit as x goes to infinity, my derivative is cosine of x minus e to the x. My derivative in the bottom becomes negative sine x plus e to the x, which doesn't look a whole lot better for us. Although I still have some number between plus and -1, minus a large number, so I still have a form that looks like negative infinity over infinity, so I could use L'Hopital again and see if it helps me. Limit as x approaches infinity, negative sine x minus e to the x over negative cosine of x plus e to the x. So it looks like we can certainly apply L'Hopital. He's just not really helping us so much in this example. So L'Hopital is going to help us sometimes, but sometimes you can apply L'Hopital and it doesn't really help us come to a conclusion in the end. But we can still apply them all day, although we wouldn't want to, it's not helpful. So yeah, there are functions that are a little wacky that just applying L'Hopital is not going to help us. And then we would have to analyze this in possibly another way. So maybe analyze how the sine function and the cosine function are changing and how that works with these guys over here.
So is it possible to solve something like that?
We could analyze it, but that would be something for us to chat about after class. So in terms of how would you analyze something like this, it's not going to be a straight calculation. It's going to be an argument about bounding functions and saying, okay, that this